Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit number 6, Lesson number 10, which is going to concentrate simply on the derivative of the sine function. As always, you can find the worksheet used in this lesson by clicking on the video's description. There is no homework for this lesson, which my students are going to be happy about, because all we're really trying to do is establish the most important trigonometric derivative out there, which is the derivative of the sine function. So let's get going on that. All right, so our first exercise really kind of walks us through this. And what I've given you is the graph of f of x equals sine x on the interval negative 2 pi to 2 pi. And I want to note that I have scaled this graph properly. In other words, 1 unit of the y-axis corresponds to 1 unit of the x-axis. Letter A asks us to draw tangent lines on the above graph at all the quadrantal angles. So why don't you go ahead and do that? Draw tangent lines at all quadrantal angles. Pause the video now if you need to. All right, let's do it. Well, the quadrantal angles are the multiples of 90. So I'm gonna put tangent lines here, here, and here. There's also quadrantal angles here, and that was supposed to be a tangent line, and that's supposed to be a tangent line, and that's one, and that's a little bit better of one, and that's my last one. Eek. Okay, anyway, I'll do a little check mark there. I'm going to go back to blue. Maybe I'll write better in blue. Letter B says, at what locations is the derivative of f of x equals sine x equal to 0? Plot these points on the set of axes below. So I want you to think about this for a second. Where will the derivative of sine be 0? And of course, it will be 0 whenever we have horizontal tangent lines. That's going to be here. So at x equals pi over 2. It's going to be here at 3 pi over 2. It's going to be here at negative pi over 2, and of course at negative 3 pi over 2. And it says to plot these. Now, in other words, I'm actually plotting the derivative now. So the derivative of sine x at pi over 2 is 0. The derivative of sine x at 3 pi over 2 is 0, etc. So those blue dots that I'm putting on are actually the y-coordinates of the derivative function. In other words, the slope is 0 at those points. Now, letter C says, given that the graph has equally scaled x and y axes, estimate the slopes at all the other quadrantal angles and plot these slopes on the axes above. So what I'd like to do is really just hone in on this one tangent line. Now look at that thing. I'm gonna draw over it in blue. Hopefully that's not going to become even more confusing. But if I had to ask you to take one shot at what that slope is, one shot, what would it be? Now, a lot of students will tell me y equals x, which unfortunately isn't a slope. But it's the right idea. The slope at that point is 1. All right? The slope at this point will be negative 1. The slope at this point will be 1, and by this point I mean here. The slope at this point will be negative 1, and the slope here will be positive 1. So let's plot those slopes. Plot a slope of 1, a slope of 0. Here I'll plot a slope of negative 1, then I have a slope of 0. Now I'll plot a slope of 1. Again, plotting a slope of negative 1, a slope of 0, and a slope of 1. So all of those points are now outputs to the derivative of sine x. So we could now connect these with a smooth curve. No reason to think it'll be anything but a smooth curve, given how smooth sine is. Whoops, missed it a little bit. But there's the derivative of sine x. And I'm hoping it looks familiar. So, take a look at letter D. It says fill in the following. Conjecture. The derivative of sine x is what? Think about that for a moment. Got it? The derivative of sine x is cosine x. Now that's a conjecture. All right, I really want to emphasize things about conjectures. A conjecture is a guess. That's all it is. It's a mathematical guess based on good evidence. In other words, I look at that graph in blue and I say, that looks a lot like the cosine graph, so I'm thinking that the derivative of sine is cosine. And what we're going to do in exercise 2 is we're going to do the proof. All right? So I'm going to scrub out all the graphs and texts in a moment. Why don't you go ahead and copy down anything you need? Okay, I'm going to get rid of it. Let's go on to the next page. All right, we're going to prove that sine x, the derivative of sine x is cosine x. This is, quite frankly, one of the most famous proofs in all of calculus. So you gotta see it. You gotta see this proof. Now, in order to do this proof, we actually need two trigonometric identities. So what I'd like you to do is take a look at letter A, point number 1 and point number 2, and see if you can remember what the identities are for sine A plus B and 1 minus sine squared A. Now, if you can't figure them out, maybe pause the video and do a little bit of an internet search. Even though that means you don't remember, it's still a good thing to be able to find the information on your own. So pause the video now and take as much time as you need. All right. Well, I'm certainly not going to derive these things for you, but the sine of A plus B is the sine of A times the cosine of B plus the sine of B times the cosine of A. All right, and 1 minus sine squared A is the same as cosine squared A. This is actually what's known as the Pythagorean identity, and it comes from the fact that when we take cosine and we square it, and sine and we square it, and we add them together, we get 1. Now I'll put that little parentheses here, although they're not necessary. So now that we have those two trig identities, we're ready to do the proof. Now, whenever you introduce a new derivative in calculus, sometimes you can get at it by little techniques like implicit derivatives, the way that we did when we found the derivative of the natural log. But many times you have to go back to the very definition of the derivative, the very definition. So remember, the definition of the derivative, and I'm going to use h here, is the limit as h goes to 0 of sine of x plus h minus the sine of x all divided by h. Now, the question is, where do we really go with that? What can we do with it? Well, one thing that we can do is we can use this trig identity in number 1 to rewrite that numerator. Now, don't forget to keep the limit. So I can say the numerator is sine x times the cosine of h plus the sine of h times the cosine of x, and then I just have that sine of x attached to the end. Right? So I just used that trig identity that we had back in letter A, subsection 1, to rewrite this quantity as this one. All right, going back to blue. So keep going. Well, take a look at the numerator now. All right. In this particular case, what I'm going to do is I'm going to take advantage of the commutative, associative properties of addition, subtraction, blah, 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 to do the following. Do you like my technical terminology? Blah, blah, blah. I'm going to rewrite the numerator as sine x cosine h minus sine x all divided by h plus sine h cosine x all divided by h. I'll just put that because the limit does apply to both of those fractions. Now all I did was take that minus sine x and bring it over to group it with the sine x cosine x, and then I broke this thing into two fractions. I hope you're okay with that. Let's do a little more work. Let's now take this fraction and let's factor a sine x out. And what we'll be left with is cosine h minus 1 all divided by h. And I'm going to just now apply the limit to both of these fractions so I can look at them separately. All right, we're getting there. Now, I want you to ignore the first fraction. I want you to ignore this piece right here. I want you to just look at this, and I want you to answer. Do you know what this limit is equal to? Think about that for a moment. Do you remember? It's equal to 1 if we are in the radian system. So that is just going to be 1 times cosine x. Now, that's what we want, right? We want our derivative to be cosine, which means in theory, all of this should head to 0 as h goes to 0. So that's the only piece left of this proof. We just have to prove the sine x is immaterial because it doesn't depend on h. We have to prove that cosine h minus 1 divided by h goes to 0 as h goes to 0. So let's just take a look at that a little bit separately. I know that we don't do a lot of proof here, but all right, now watch what I'm going to do. All right, what I'm going to do is I'm actually going to pull something very tricky. I'm going to multiply top and bottom of this expression by cosine h plus 1. And I have to write a little bit smaller here because this is one honkin' large proof. Now, whenever I multiply two conjugates, I always get a squared minus b squared. All right, so in the numerator I get cosine squared h minus 1. But notice, what that is going to be, right, will be negative sine squared h. Right? That's really just using this thing. All right, divided by h times cosine h plus 1. We're almost there. I got to sneak it in right here. I apologize that it's at the bottom of the screen. I'm now going to break this thing up as the limit as h goes to 0 of sine h divided by h times negative sine h divided by cosine h plus 1. No problem. Really, this limit's all in parentheses. This is going to go to 1, but this is going to go to 0, and this is going to equal 2. So ultimately, I'm going to get 1 times 0, which is 0. And that's what I thought. So after all is said and done, this limit becomes 0 plus cosine x, which equals cosine x. Now, I want to just pause for a minute. Just pause for a minute. In the last lesson, we saw that the limit of sine of theta divided by theta as theta went to 0 was equal to 1 if we were in the radian system. All right? As a consequence of that, right here, we got that thing to be 1. I don't know if you remember this, but when we did it in radians, we got like 0.0175, really ugly, which actually was pi divided by 180. Because that limit of sine h divided by h is equal to 1, we can say the derivative of sine is cosine. If we were working in degrees, then the derivative of sine would be pi divided by 180 times cosine. And that would get awfully ugly. Very, very ugly. We don't want to do that. All right? So that's it. That's the derivative of sine x. It's cosine x. That is one honkin' big proof. Sorry about how ugly it turned out to look. All right, play it again and again and again to enjoy it. It really is one of the most famous proofs in all of math. I'm going to scrub out the text, so copy down anything you need to now. Okay, here it goes. All right. Now, if the universe was elegant and things worked out beautifully, then what would happen is that what we would find is that the derivative of cosine would be sine. All right? And we can test that now. We've got this numerical derivative command on our calculator, which all the students in my class know how to activate. On the TI 83 or 84 Plus, it's the math button, and then it's option 8, which gives you what's known as the numerical derivative. I'm not going to open up the calculator right now to pull that out. I don't think that there's any need to. But what I'd like you to do is pause the video right now and use the numerical derivative command on your calculator, make sure you're in radian mode, to find out the derivative of cosine x at 0, at pi over 6, and at pi over 2. And then we're going to see, well, is that sine of 0, sine of pi over 6, sine of pi over 2? Go ahead, see what happens. Okay, that should have taken you a little bit just to type everything in, and I hope you did do it. Otherwise, you're kind of missing out on something. But what you would find is you'd find that the derivative of cosine x at 0 is 0. And sine of 0 is, of course, 0. So far, so good. You know, we want this to be equal to this. But the derivative of cosine x at pi over 6, on the other hand, at pi over 6 is negative 1/2. Sine of pi over 6 is a positive 1/2. I'm going to put a giant red X. So that doesn't work. So right now, unfortunately, we know that the derivative of cosine is not sine. But maybe it's something that we can use. If I find the derivative of cosine x at pi over 2, what I would find is negative 1. And of course, sine of pi over 2 is positive 1. Again, showing that the derivative of cosine is not sine. But what's our conjecture? Right? Write down a final conjecture. What is the derivative of cosine x? Pause the video now. Okay. The derivative of cosine x is not sine x, but it is certainly negative 1 times sine x. All right, we're not going to actually prove that. To do a proof of cosine would be very, very similar to the proof of sine, and that negative would kind of come out in the wash, so to speak. So there are two major things you want to come out of today's lesson with, and that's basically it, really. You want to come out with the fact that the derivative of sine x is positive cosine x, and unfortunately, the derivative of cosine x is negative sine x. And the only thing that's unfortunate about that is the introduction of the negative. And that's it. All right. So make sure that you know those two derivatives. Get a feeling for the proof, although you won't have to probably reproduce it in my class at least. I don't know about other classes that might be watching this. I'm going to scrub out the text now. And let's finish up. All right, well, that was a pretty short lesson, I know, but it was intended to be that way because what we were really trying to get at was how to just simply find the derivative of the sine function. Now that we know the derivative of the sine and the derivative of the cosine, we're going to be able to find the derivative of all the other 4 trig functions pretty easily. But we'll take a look at that in the next lesson. For now, this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.